Okay, so in this example problem, we're going to be looking at Reynolds Transport Theorem and specifically the Newton's second law or conservation of linear momentum variation of Reynolds Transport Theorem, looking into how much horizontal force is required to hold this flat plate statically in place against this incoming impinging jet of water from this nozzle. Now, looking at the geometry of the problem, again, we have a nozzle and it is shooting out a stream of water that's hitting this flat plate symmetrically, such that you have a stream of water going down and you have a stream of water going up. This green box is our control volume, and these red arrows represent our cross-sectional velocity profile at those locations. So to begin, let's look at some of our assumptions. One, we're looking at a steady system, so no time-varying behavior. Two, we're looking at a constant density flow, so a flow that is incompressible and isothermal. Three, we're looking at symmetric impingement, so the velocity at 2 and the velocity at 3 are equal, the average velocities, and the area at 2 and the area at 3 are equal. It's a simplification, but it's there to kind of make the problem a little bit more manageable to solve. 4, XYZ is inertial, so the control frame is inertial, so this is a non-accelerating control volume, which means we can apply Newton's second law in its standard form. 5, the velocity and pressure profiles at A1, A2, and A3 are uniform and unidirectional, so A1, A2, and A3, these velocity profiles are approximately equal and unidirectional. And 6, we can neglect the weight of the assembly. So we're going to neglect the weight of the flat plate, the water, the air, all of that stuff within the control surface, within this control volume. So what we need to do is find the horizontal force required to hold the plate in place. So as we shoot this stream of water at this flat plate, the water is going to want to induce motion in the flat plate in the direction of the stream of water from A1. We need a horizontal force to keep that flat plate in place to bear against the momentum of that jet. And we need to determine what that horizontal force required is. And this could be something useful. For example, how strong does my cross member here need to be to withstand the stress associated with statically keeping this flat plate in place against some variation or permutation of water streams or other fluid streams. Our givens in this problem, we're going to be looking at a V1 equal to 12 meters per second. We're going to be looking at an A1 equal to 0.0125 square meters and a rho of 999 kilograms per cubic meter, or in this case, essentially water. Now we're going to the equation slide. I'm not going to use this video to derive these equations. I'm just going to keep them on the screen for reference. But we have gone over Reynolds Transport Theorem before, and we've gone over conservation of mass before. We haven't gone into the conservation of linear momentum variation of Reynolds Transport Theorem very much, if at all. But essentially the way it's derived is very similar to the way that you derive the conservation of mass variation, where you have your system variable of interest n is equal to the linear momentum vector p, and therefore eta, which is n per unit mass, is equal to the linear velocity vector v. You plug those into Reynolds Transport Theorem while realizing that dn dt system essentially translates to the net external force on the control volume, and you get this vector equation right here. And because it's a vector equation and we're working in Cartesian space, you can split it into 3 components. We're primarily interested in the x component in this problem because that's translating to the horizontal force as we've established in our control volume coordinates, but we've also written out the y and the z components for reference. We also have our conservation of mass equation, which we will see is not super useful for this problem, but we will work it out for practice and to see that our symmetric assumption is essentially behaving the way that we think it should, right? Because what we believe we should see is if we've prescribed V2 and V3 to be equal and A2 and A3 to be equal, we know that the volumetric flow or the mass flow rate through 2 and 3 should be equal. They should be symmetrical as well. And conservation of mass will tell us that. And if that's not the case, then there's something we're not understanding. So let's go to the third slide here. And what we're going to be looking at is the free body diagram of this system or the external forces on the control volume. So we have a few forces here. We have the pressure force from the fluid at A1, the pressure force from the fluid at A2, and the pressure force from the fluid at A3. You have our atmospheric pressures on every side of the control volume. And you see we have little cutouts for where we have fluid running through, and that's because those cutouts, the pressure at those cutouts is covered by the water stream, and everywhere else it is just atmospheric ambient pressure. We have our reaction forces that go through this flat plate. So as we cut this flat plate with the control volume, we have a horizontal reaction force Px and a vertical reaction force Py. And we also have the weight of the assembly, which we know we're going to neglect. So one thing to note here is we have no shear components in the free body diagram at A1, A2, or A3, and that's because the profiles are uniform and unidirectional, so there is no mean velocity gradient on this control surface to create a shear force that would be accounted for in this free body diagram. Now what we're going to do is apply our conservation of mass. And again, this is just kind of a basic check to see that our symmetry assumption makes sense and does what we think it does. So when we write out our conservation of mass equation, we know that our first term, our time varying term, is 0 because we have a steady system. So we just have this integral over the control surface of rho v dot dA, which essentially represents the mass flux through the control surface, the net mass flux through the control surface, whereas this term right here represents the time rate of change of mass within the control volume. So now we know we're just dealing with a surface integral. So one thing to note here is we can simplify this integral rho times the integral over the control surface of v dot dA in a couple of ways. The first way is we note that the subsections of the control surface that we really care about are sections 1, sections 2, and sections 3, right? There is no flow over the other sections of this control surface. There's only flow over sections 1, sections 2, and sections 3. So the integral over this control surface for the areas where there is no flow approaches 0, right? It is equal to 0. So we're only examining the control surface integral where there's actually flow across the control surface. So now we just need to explain, where do these v dot a's come from? How do we get v dot a here? How do we get v dot a from this integral, which has v dot dA? Well, let's just kind of work this out to explain it. If we have an integral over our control surface of v dot dA, and we know that we have 3 terms that we really care about, we've just gone over that. Cross-section 1, v dot dA, plus cross-section 2, v dot dA, plus cross-section 3, v dot dA. We know that these can be simplified as following. Well, on cross-section 1, right here, what we end up having is something that looks like this. v1 dot dA1 plus v2 dot dA2 plus v3 dot dA3 plus dot dot dot, and that's for cross-section 1. And then we have the same thing for cross-section 2 and the same thing for cross-section 3, right? So now what you realize is for each cross-section 1, 2, and 3, the velocities within them are equal because the velocity profiles are uniform and unidirectional. So effectively what you can do is pull out these velocities out of each sum. So v1, v2, v3, all the way through vn for each cross-section are all equal within their respective cross-section. So the velocities are not equal amongst the cross-sections, like the v here is not equal to the v here is not equal to the v here necessarily, but the v's within these summations within each cross-section are equal. So effectively what you can do is pull them out of the sum, and then you have this v dot the sum of these dA vectors. What is the sum of the dA vectors? It is the area vector for that cross-section. So this is where effectively you get your v dot a, because you're pulling out your velocities from this sum. It's this overall velocity dot the sum of these differential area vectors, which is equal to the overall area vector. So that's how you're getting your v dot a's. It only works because our velocity vectors are uniform at each cross-section. So the next question is, how do we get these signs? Well, remember from the derivation of Reynolds Transport Theorem that the area vector is defined as positive outward, right? The normal area vector is defined as positive outward. So whenever your velocity vector is in the same direction, your dot product is positive. Whenever your velocity vector is in the opposite direction, your dot product is negative. So let's look at A1 here. At A1, our velocity vector is going in and our outward normal area is going out. So the velocity vector and the area vector have opposite directions, so the dot product is negative. Here at V2, we have a velocity vector that is outwards and an area vector that is outwards, same direction, dot product is positive. And at A3, we have a velocity vector that is outwards and an area vector that is outwards, same direction, so the dot product is positive. And then effectively what we get is that the volumetric flow rate through section 2 and through section 3 are indeed equal, and that is equal to half the volumetric flow rate that goes through 1. So in other words, half the volumetric flow rate that goes through 1 goes to section 2, and the other half goes to section 3, which is exactly symmetrical and what we expect for a symmetry condition, so this result makes sense. Now we're going to apply the conservation of linear momentum equation as we see here, and the same logic from the conservation of mass slide applies. The same dot product logic, the same assumptions logic, all of it. All of that applies here for the conservation of linear momentum analysis as well. So the first thing we need to do is find the sum of the external forces on the control volume. So our force balance in X, we have P infinity A infinity L plus P1A1 minus PX minus P infinity A infinity R. If we go to the free body diagram, we see P infinity A infinity L is the atmospheric force that acts on the left side of the CV, and it acts to the right, so it's positive. We have P1A1, which acts to the right, so it's positive, and that is the force from the pressure of the fluid at section A1. We have P infinity A infinity R, which is the atmospheric force on the CV from the right. It acts to the left, so it's negative. And we have PX, which is our reaction force, and we assume that that acts to the left, so it's negative. And these signs are all relative to the coordinate system that we defined on the control volume XY right here. So that overall force balance is then equal to the conservation of linear momentum equation. We know that this time derivative term goes to 0 because it's a steady system, and therefore we're just left with this flux term, integral of the control surface of u rho v dot dA, very similar to the conservation of mass analysis we just did. So a couple of notes about this equation. We're not going to repeat too much from the conservation of mass analysis, but again, there's only one section of the control surface that we care about, and that's section A1, and that's because that's the only section with x momentum crossing the control surface. So we only have one term here, and that represents A1. We have our dot product again, v1.a1, and again, the velocity vector goes in, and the outward normal area goes out, so the vectors are of opposite directions, so the dot product is negative. So that's why you get this negative v1a1. And then you have the x component of velocity at section 1. Well, because the velocity at section 1 is purely in the x direction, the entire velocity vector is the x component at that section. So u1 is equal to v1. Now note that u1 or u is a component of the velocity vector, so it can be negative. However, in this case, it's acting to the right, it's flowing to the right, so it is positive. So this is really positive v1, but this could be negative. So if this was flowing to the left, this would actually be negative v1. Just keep in mind, it just so happens to be positive v1 in this case, but it is a component, so it could be negative. Now, when we simplify this term, we get negative rho v1 squared a1, and this negative rho v1 squared a1 represents the thrust of the impinging jet. So basically, the forces acting on the flat plate need to be such that we can counteract the thrust from that impinging jet, and that thrust is quantified by this negative rho v1 squared a1. Now, a couple of notes about this force balance so we can simplify it a bit. P1 is equal to P infinity. Why is that? Because in an ambient jet, the pressure of that jet is equal to the ambient pressure. So in this case, P1 is equal to P infinity. Also, A1 plus A infinity L is equal to A infinity R. So with those two things in mind, you can see how we go from P infinity A infinity L plus P1A1 to P infinity times the quantity A infinity L plus A1. And we know that A infinity L plus A1 is equal to A infinity R. So P infinity times that quantity is equal to P infinity times A infinity R. That cancels with the actual original P infinity A infinity R. And we're just left with negative Px, right? So negative Px is equal to negative rho v1 squared a1. The negative signs cancel, and you get Px is equal to rho times v1 squared a1. You plug in your givens, and you get that Px is equal to 1.7982 kilonewtons acting to the left, right? So we got a positive value for our Px, which indicates that we assumed the correct direction. So Px has to equal 1.7982 kilonewtons acting to the left to counteract the impinging jet from the nozzle. Okay, so that should be it for this video. Thank you very, very much for watching. I really appreciate it, and I will see you next time.